All right, in this video, we're just going to review the practice questions using the solar system data chart on page 15 in our reference table. So that's going to be really the key to this whole thing. And make sure you have answered these questions on your own first, or at least all the ones that you were comfortable answering before you go back and watch this here. So pause it if you haven't yet had a chance to start this. All right, so let's start taking a look at our first question. First question says, which object in our solar system has the largest equatorial diameter? Since they said object, it could be any one of these things. And all I have to do is look at the equatorial diameters and realize very quickly that the sun, by far, has the largest equatorial diameter. That simply means it's the biggest object in our solar system. Number 2 says, which object in our solar system takes the least amount of time to complete its orbit around the sun? So as soon as I see the time to make an orbit, I have to think of the period of revolution. That's how long it takes to make one orbit around the sun. So if I were to look at all of these options here, and I look at the period of revolution, well, if we go down the list, Neptune, you have to be careful, the units are different. We have days and years. Neptune takes the longest time. It takes 164.8 years to go around the sun, so I'm simply going to say it's Neptune for that one. Now for number 3, what object averages a distance of 778.3 million kilometers from the sun? So we go to the column that says mean distance from the sun. Those units are in millions of kilometers. And I'll just follow it down till I match the number, and that would be Jupiter, our Jovian planet there. So we'll go ahead and say Jupiter for this one. Number 4 sometimes is one of the sneakier questions in this. It says, what object is 386,000 kilometers from the Earth? Now, they're saying from the Earth, not from the sun, so this is mean distance from the sun. But if you look carefully, in parentheses down here, we have 0.386 from Earth, and 0.386 of a million equals 386,000 kilometers. And since it's from the Earth, that was also a clue. It had to be close to the Earth, so the answer here is actually the Earth's moon. We wanted to point that out because it's a little subtle detail, but that's where the distance from Earth to the moon can be found, and it's an average distance. We're going to find out all of these are averages. The planets orbit in a shape known as an ellipse. They're not perfectly circular. Number 5, is a day on Mars or a day on Earth longer? So since we're dealing with day, we want to look at period of rotation. So I'm going to look to the period of rotation at the equator. On Earth, 23 hours, 56 minutes, and 4 seconds, and notice Mars is a little longer, 24 hours, 37 minutes, and 23 seconds. So a day on Mars is slightly longer. For number 6, we want to know which planet is closest in size to the Earth. Now, since these are all spherical, the diameter is going to be the best way to compare the actual size of them. So Earth's diameter is 12,756 kilometers across the equator, and the closest one is actually the one right above it. It's going to be Venus, which has the most similar size to the Earth there. All right, now number 7 hopefully is an easy one. We just want to know which planet is the most dense. I'm not sure if dense is just a word, but the most dense. So we're going to go ahead and look at the chart. We're looking at the numbers. The highest number is right here, 5.5, and when you know it, that's Earth. So we live on the planet that has the highest density. And the planet that is the least dense, we go on down the list. There it is, 0.7. That is Saturn. The density of Saturn is so low that if you could somehow get a sample of it, it would actually float in water. Now for number 8, we want to know how many times more massive is Neptune when compared to the Earth. So we're going to use the mass column for this. And notice they have Earth set to a mass of 1. That means anytime we see one of these numbers, it's telling us how many times more or less massive that planet is than the Earth. So when I look at Neptune, the number for Neptune is 17.15. Well, 17.15 times 1 is just 17.15. So the planet Neptune is 17.15 times more massive than the Earth. We don't have to do any fancy math or anything like that. Whatever that number is tells us how many times more massive it is. Now, number 9, which planet is the largest? And we do have to be careful because they said which planet, so we can't put the sun as an answer because that's a star. So if we ignore the sun and we look at all of the other equatorial diameters, the biggest planet is Jupiter. All right, and for number 10, we want to know which planet rotates at the slowest rate. So we have to look at our period of rotation, and you do have to be careful because some of them are in days, Some of them are in hours, minutes, and seconds. Some are just hours. So we start kind of looking through, and the one that rotates the slowest is going to be the one that has the longest period of rotation, and that is Venus, which takes 243 days to make one rotation. So Venus, by far, is the slowest. And then which planet is the fastest? We have to be a little careful here to make sure we're watching our numbers. If we look right here, 9 hours, 50 minutes, and 30 seconds for Jupiter, that is the fastest rotating planet. Considering Jupiter is the biggest, that thing's really moving around. Now, number 11 has to do with the topic we're going to be getting to soon, eccentricity. We want to know what is the eccentricity of Jupiter. For now, all you have to do is look up Jupiter, find eccentricity, and you would simply just write the number there. So the eccentricity of Jupiter is 0.048. And then for number 12, which object has the most eccentric orbit? So simply what we'd have to do for that is we're at that eccentricity column again, and we're simply going to look for which number is the highest. Now, if we go through all the numbers here, they're not in any particular order, they're kind of random. We check out this guy, Mercury, 0.206, that is the largest eccentricity. So that is the most eccentric planet. What that means is its orbit is the most stretched out. We're going to explain that in a future lesson. Now, number 13, also something we'll see in a future lesson, which planet's orbit is closest to being a perfect circle? Now, an object that's a perfect circle would have an eccentricity of 0.000, exactly 0. So I just have to figure out which planet has a number closest to 0. And there are two that are close, Neptune and Venus. 0.007 is the closest to 0, so it turns out Venus is the one that has the most circular orbit. And it's because its eccentricity is the closest to 0. All right, 2 more questions to go. There's 2 on the back side, so if we flip it over here. Number 14 asks us to compare the densities of the terrestrial planets and the Jovian planets. All right, and how do these densities between these 2 classifications differ? So you have to remember the terrestrial planets are Mercury, Venus, Earth, and Mars. And if we look at the densities of those, we have 5.4, 5.2, 5.5, 3.9. If we look at the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, the densities are 1.3, 0.7, 1.3, and 1.8. So those densities are definitely lower. So we could simply say the Jovian planets are less dense. So I'm just going to draw a little arrow here. So you can say the Jovian planets are less dense, the terrestrial planets are more dense. Either way, it works out. And then for our last question, we want to explain the difference between an object's period of rotation and an object's period of revolution. Well, rotation is the spinning on the axis, and that's what gives us day and night. So that's when the planet spins on its axis. And period of revolution is how long it takes to orbit the sun. So that's what would give you a period of seasons, if you want to think of it that way, on a planet. So again, revolution is the path around the sun, and for Earth that would take a full year. Rotation is you're spinning on the axis, and that's what gives you day and night on that planet. So on Earth it would be about 24 hours. And it's going to be different for each one of these, so you'd have to be able to look them up on the chart. All right, so that's it for this practice. Obviously, if there are any questions, make sure you let me know, and we'll move on to our next topic.